Swayam Prabha. Digital India. Educated India.
Right? And from here to here, although you had tried to turn on S1 right from the beginning, but S1 will turn on only from here, where the current is in the positive direction. You may give the pulses even before that, but S1 will not be able to turn on until D1 is conducting. D1 will be conducting during this portion. So when D1 is conducting, there is no way S1 can turn on. Please note that S1 will be reverse biased when D1 is conducting, because when D1 is conducting, I am going to have positive here and negative here. And the switch that you connect here will be in this direction. This is how it will be. So you want basically VCE to be positive. That will not happen when the diode is conducting. So D1 will be conducting for this duration and S1 will be conducting for this duration. D2 will be conducting here, S2 will be conducting here, again D1 will be conducting here, and so on and so forth. So the steady state here corresponds to the minimum currents remaining at the same value cycle after cycle. Similarly, maximum currents remaining at the same value cycle after cycle. Rather half cycle after half cycle. So you are going to have this value to remain the same and this value will be remaining the same. I minimum and I maximum will remain the same cycle after cycle. That's what you would see. That is what is known as steady state. There is nothing like a normal DC current which is going to assume a fixed value. That's not going to happen, right? So this particular circuit consists of only 2 switches and 2 diodes, and although your input supply is VDC, what you get as the output is only VDC by 2. And when you are having VDC by 2 actually being delivered, if this switch is a short, for example, please note that this positive is connected here. When this switch is not conducting, you are going to have this positive connected here directly and this is negative here, which means VDC will come across the non-conducting switch. That is twice the voltage of what it can deliver. So a half bridge, normally each of the devices will face a stress corresponding to the twice the voltage of whatever it could deliver as output. So you are going to see that if it is delivering VDC by 2, VDC will be the voltage stress or voltage that it has to block whenever it is in off condition. This is one of the problems of half bridge, because if I am talking about kilovolts level of an inverter, I do not want really to increase the cost of those devices by simply having the rating to be increased twice as compared to what it can deliver. So half bridge is generally used only when I actually am going to use it for smaller rating, not for very large rating. Normally in larger rating we hardly ever use half bridge. We will only use full bridge in that case. So let us try to take a look at full bridge VSI. Again we are talking about single phase. So we are looking at a DC voltage source, and then I am going to have 4 switches, which is similar to that of whatever we studied in full bridge DC to DC converter. It's exactly similar. And there will be feedback diodes in these cases also. These diodes are known as feedback diodes because they feed back the energy stored in the load inductance. So these are feedback diodes. So each of them is going to be connected to a feedback diode in anti-parallel. And please note that these diodes have to be fast acting. They can't be power frequency diodes. We talked about 2 or 3 different types of diodes. You remember? We talked about power frequency diode, we talked about fast recovery diode and Schottky diode. So fast recovery diodes have to be used in this case because they have to essentially work very quickly. So unless they act very quickly, it's going to be difficult, especially if I'm using in PWM. So that's the reason why what we use will be normally fast recovery diodes. So the load is going to be connected here. So I can name this as S1, S3, S2 and S4. Now, if I am looking at positive half cycle, which is actually going to make the current flow in this direction, S1 and S4 have to be turned on, right? And after S1 and S4 are turned off, if I want the current to flow in the same direction, right? I want the current to flow in the same direction means I'm going to have these two diodes, right? This diode and this diode conducting with the current direction being the same, but please note it is feeding back the energy to the battery, right? So the battery will get charged, it is like regeneration. So we are going to have the current flowing in the same direction with the diodes feeding back the stored energy of the inductance, load inductance back to the battery. So let us again try to draw the waveform for, so let us say this is the positive half cycle and this is going to be the negative half cycle and again positive half cycle and so on. So let us say this is V load, right? Now if I am looking at the current, maybe it is starting from some negative value and then it is reaching the maximum value like this, and again it is going to be something like this and so on and so forth. This is how the current is going to be, right? So during this particular duration, I am going to have actually, during this duration, I am going to have S1 and S4 both conducting, right? That's why the current is also positive and voltage is also positive, which means the power is flowing from the DC side into the AC side. The power is positive. It is being consumed by the load. When voltage as well as current are positive, it's going to be consumed by the load, right? That's why the current is increasing. Now during this portion, I'm going to have the current flowing. Let me try to name these things. This is D3 and this is D2. So I'm going to have D2 and D3 conducting during this portion. So the voltage is going to remain and the voltage is going to become negative because I am having essentially the positive being connected through the diode here and negative being connected through the diode here. So the voltage has reversed its direction. Originally, when I looked at the voltage, S1 was connecting positive here and S2 was connecting the, S4 was connecting the negative here. Right? Whatever I have mentioned in green is when I had S1 and S4 conducting. Once they have gone off, I'm going to have D2 and D3 taking over, which is going to have a negative voltage. Right? And similarly, I'm going to have S2 and S3 conducting here, and I'm going to have D1 and D4 conducting here. If I may call this as D1 and this as D4. So D1 and D4 are going to conduct here. If I try to look at what is the kind of current I'm going to see from the source side. So this is load current and this is load voltage. Right? So what is the kind of supply side current that is going to come up? So when I am looking at S1 and S4 conducting, right, I'm going to have essentially the current going like this. This is how it is going to be. Whatever is S1 and S4 current, it is going from the supply towards the load, right? Whereas when I am looking at this current, this portion of the current, that is essentially flowing from the load into the supply. So it is in the opposite sense. So I have to show it as though this is essentially coming until here, maybe somewhat like this, right? And again, when S2 and S3 are conducting, I'm going to have the current essentially going like this. And again, I'm going to have the current being fed back to the supply whenever I have the diodes conducting. So this will be the supply current. So this is essentially, if I call this as IS waveform is going to be somewhat like this. I hope you get this. Whenever I'm going to have the devices conducting, I am having the power flowing from VDC to the load. So it is in positive direction. The current is in the positive direction. And whenever the diodes are conducting, it is actually flowing back from the load to the supply itself. It is trying to replenish the battery. So this is going to be the kind of supply current that we are going to have. So battery is getting charged and discharged alternately in this particular case when I'm going to have RL load. And if I try to look at any of the devices, what it has to block, it will be blocking VDC itself. You can analyze and you can definitely find out that in full bridge converter, they are not going to be rated for more than VDC. That is the way normally our full bridge VSI works. So full bridge VSI is normally employed in all larger power rated circuits. They are very commonly used in many of the larger power rated circuits. But sometimes, if I'm going to have 20 kilovolt or 30 kilovolt as the overall voltage rating of my circuit, it might be sometimes difficult to just employ a pair of devices. So you might have to employ many of them in series. Rather than that, we sometimes employ something called multi-level inverter. I'm just introducing the terminology. I'm not going to go in depth into this because this is being researched extensively now. So I thought at least I should introduce you to what is a multi-level inverter. So in multi-level inverter, let us say I have one inverter here, right? So this is one inverter. I can have one more inverter like this. So if each of them is producing, let us say 250 volts approximately, by connecting them in series, I would be able to produce 500 volts. Right? I would be able to definitely produce larger amount of voltage. And I can also control each of them such that maybe rather than getting a complete square voltage, if one of them is conducting for a longer duration and the other one I make it conduct only for a shorter duration. I can make it closer to a sinusoid. I can have multiple number of steps like this. I can make basically a stepped voltage waveform which will be emulating somewhat a sinusoid. I'm not saying this is exactly a sinusoid, but I would be able to get closer and closer to the sinusoid provided I have multiple levels of voltage source inverters like this. So now what I can do is, this is one end of the load terminal, so let me take that out, and from here I can connect it to this, and from here I can connect to the load. So here I can connect my load. Right? I'm essentially connecting the two outputs in series. You imagine whatever we did in auto transformer, something similar. What we are doing is essentially connecting one end of the load here, the other end of the load here, and in between we are connecting them in series. That's it. So this will allow me to get twice the voltage of whatever is the voltage that I am applying here and here. But please note, I have drawn two independent voltage sources. I can't connect them also together. Either I need to provide isolation on this side between the two voltage outputs, or I need to provide isolation on the input side. Either on the input or on the output, I need to provide isolation. Otherwise, it will be a dead short, right? So this is typically used whenever, for example, solar water pumping system, where I may have each of the solar cells having very small value of output. I can connect two solar cells independently to the two inverters, connect them in series, and together I can give it to a motor. That is a possibility, right? So if I have multiple number of this, then I call them as cascaded H-bridge. Each of these full bridge inverter is generally called also as H-bridge configuration. So we call this as cascaded H-bridge multi-level inverter. So each of them can function independently as a single phase inverter, no doubt. So the major advantage I can visualize in this case is, if I have 5 such inverters connected in series, one of them conk out, I need to essentially have in the inventory multiple number of the single phase inverter. Remove the faulty inverter, put the good inverter. You can do that. So it is like parallel operation of transformer, what we talked about earlier in electromechanics course. We said that rather than using 20 kVA transformer directly, you can use two 10 kVA transformer in parallel. So what backup you store is only 10 kVA, not 20 kVA. So that way, it also reduces the rating of the backup. That is one of the major advantages we have in this cascaded H-bridge multi-level inverter topology. One more thing is that each of these switches need to be rated only for VDC, not 2 VDC. Each of these switches need to be rated only for VDC. There is nothing like you have to rate them for a higher voltage. So that way it becomes much more comfortable to construct smaller units and then put them together, right? So this is a very upcoming area which is being researched extensively, multi-level inverters, right? Now let me just go over to the 3-phase inverter. After discussing all of them in square wave, then we will go for directly discussing them with different PWM techniques. So 3-phase inverters normally are actually constructed in half-bridge fashion. That is, I will not have 4 devices. Instead, I will have only 2 devices for every phase. So typically, I'm going to have something like this. This is my VDC. So I'm going to have one switch, another switch. This is belonging to A phase. I'm going to have one more switch and one more switch. This belongs to B phase. Then the third leg, which belongs to C phase. And numbering we will do very similar to what we had done for the rectifier. So I will call this as S1, this is S4, this is S3, this is S5, S6 and S2. Of course, each of them will have diodes as well in parallel. They will have diodes as well in parallel, no doubt. And we are going to connect from here the 3 loads. And I'm going to take star connected load for now. I'm going to leave the delta connected load to be analyzed by you guys. You guys would do it. Okay? So I'm going to do it for star connected load. So this is one load, this is the second load, and this is the third load. So let me call this as ZC, ZB and ZA. Because S1 and S4 I want to take it for A phase. Right? There are two modes of conduction. Normally we analyze in a square wave inverter for 3-phase case. Each of the devices can conduct for 120 degree or each of the devices can conduct for 180 degree. Either way is fine. So we call one of them as 120 degree conduction mode, the other one as 180 degree conduction mode. These are the two types of conduction which we would be analyzing. So let us say we are talking about 120 degree conduction mode to start with. So first of all, let me draw the A phase, B phase and C phase voltages, right? Then we have to draw the line to line voltages as well, because we would like to definitely know how the line voltages are. Always the load need not be star connected, but nevertheless we should analyze for both star as well as delta configuration, because the loads could be connected in either way. But in either case we should know what is the load voltage as well as the phase voltage as well as line voltages. So if this is the way it is, and let us say I'm going to have probably, let me call this as the 180 degree point, this is 360. So this is 0, this is 180 degree, this is 360 degrees. Okay. And then I'm also drawing 60 degree intervals like this. So I'm going to have in all probability, let us say one is going to conduct for some time like this. Okay. So if one is conducting like this, and we are talking about 120 degree conduction. So obviously 3 has to start conducting from here until this point. This is how it will be. And I'm going to have 5 conducting from this point until here. Right? They are all 120 degrees shifted from each other. Right? This is how it is going to be. So when I am having 120 degree conduction mode, I will have in all probability 1 and 6 overlapping with each other. I definitely need an overlap, otherwise I am not going to have the return path for the current. So I will have essentially the current going from S1 through ZA and returning through ZB through S6 back to the negative side. So what I get as the voltage overall, what I get will be essentially VDC across whatever is my 1 and 6. So that is VAB, that is going to be VDC value itself. So I am essentially going to have this, let us say along with this, so this is S1, this is S1. So along with this I have to have S6 conducting. Right? Clearly I have to have S6 conducting. And under this condition, so if S6 is conducting here, S6 must have conducted here also for 60 degrees, clearly. And I should have a 60 degree dead band here, like what we had in the case of rectifier without commutation overlap. I'm essentially drawing the pulses rather than drawing VA, VB, VC. I should say first of all I'm drawing the pulses. So when I draw the pulses, I'm essentially going to have the pulses that are delivered to any of the devices somewhat like this, right? So when S1 is conducting, it is this way, this is S3, and along with S3, initially S2 will be conducting, so I should show from here, I will have S2 conducting for 260 degree duration.